The inspiration for this project comes from the idea of using a quadrotor to assist in the search and rescue of avalanche victims. Two challenges that exist when flying an aerial vehicle in a mountainous environment are wind turbulence and obstacle avoidance. I modeled wind turbulence using the Dryden model. The Dryden model represents the linear velocity components of wind gusts as spatially varying stochastic processes, characterized by their power spectral densities. The aerodynamic forces acting upon the quadrotor were approximated using a single, flat-plate airfoil. This model summarizes lift and drag forces acting on a body as a single normal force located at the aerodynamic center of the plate. I compared two control approaches. The first approach was to perform offline trajectory optimization using direct collocation and combine it with LQR stabilization. The optimization includes initial and final state constraints, thrust limit constraints, and obstacle avoidance constraints. The cost function being minimized is time to target state. The LQR regulator policy was derived by linearizing the quadrotor dynamics along the nominal trajectory at each time step and solving for the optimal policy to regulate towards the nominal trajectory. The alternative approach was to perform linear model predictive control. This method simplifies the trajectory optimization problem by linearizing the dynamics and removing nonlinear constraints. This makes the problem convex, allowing the optimization to be solved more quickly, enabling real-time control. This comes at the cost of a simpler approximation of the dynamics and an inability to handle nonlinear collision avoidance constraints without additional work. The offline optimization was performed without knowledge of the wind turbulence. However, the controller performed well with light turbulence, which was surprising. This is because the magnitude of the disturbance was small enough that the LQR approximation of the system dynamics was still valid. With severe turbulence, the actual dynamics deviated too far from the dynamics used by the controller, so the quadrotor crashed and burned. My linear MPC control method produced a steady state offset from the target state, which I was unable to identify the root cause of. Analyzing its response to increasing wind turbulence, you see that with light turbulence, it reaches the target state plus offset with slight deviation. However, with severe turbulence, it is driven into the ground. This is the result of the thrust limits saturating. Doubling the thrust limits and increasing the state penalty by 10x resulted in a control policy that was able to reach the desired state, accounting for the offset, with some moderate deviation. This policy performed much better under severe turbulence than the first approach.